Okay, so the next talk is going to be on embedding hindsight reasoning in separation logic, and it's by Sebastian Wolff.
Thank you for the introduction. So, generally speaking, we are interested in verifying programs, and this equality from the late 70s suggests that we can do that by verifying algorithms and data structures separately. And in this work, we are interested in verifying concurrent data structures using separation logic. On top of that, we strive for automation, meaning that we are ultimately want to have tools that automatically generate set proofs for us. To better understand what the challenges in verifying concurrent data structures is, I would like to show you how concurrent set implementations typically answer membership queries. To that end, I want to show you how this happens in this example in a set which contains the values 3 and 7. This concurrent set here is organized as a sorted single linked list of nodes that contain the values 3 and 7, plus some sentinel nodes minus infinity and infinity. And we're trying to figure out whether or not the value 5 is contained in the set. And what implementations do to do that, to find that out, is they traverse this list. And whenever they traverse to a new node, they will inspect this node. And in this case, the traversal will find the value 3 and decide to continue its traversal because it has not found the value it's looking for yet. But because this is a concurrent data structure, it is subject, or this traversal is subject to interference. So interfering threads might alter the data structure. For instance, they could remove 3 from the set, effectively unlinking the node. They could also insert new values. For example, they could insert the value 5 that the traversal is looking for. However, the traversal is completely unaware of these concurrent updates, so it will simply continue its traversal and finally reach the node containing value 7. At this point, it concludes that 5 is not in the set because it traversed from 3 to 7, and by the sortedness of the list, it knows that 5 cannot be in the set, although, or it concludes that 5 cannot be in the set, although it has been inserted in the meantime. We are perfectly fine with this kind of outdated results that the membership query gives us because it's still linearizable. Linearizability asks that the answer we give was true at some point. So specifically in this example, what we need to show is that the value 5 was not contained in the set at some point during the traversal. The main challenge in verifying this kind of data structures is to locate this point in time, the linearization point. And it is so challenging because this linearization point can be what we call non-fixed. So its occurrence can depend on the interferences that the traversal is subject to, and it can even occur during or while the traversal is not executing. So it can occur while another thread is operating or taking a step. So how do we prove data structures with such non-fixed linearization points? The state of the art gives us 2 techniques to deal with that. The first would be prophecies or prophecy variables. And the intuition here is that the prophecies would predict the interference up front so that you kind of fix the non-fixed linearization point ahead of time. You can think of that as kind of an eager case analysis that you do. On top of that, you will use custom resource algebras to capture the structural invariant of the data structure and to pass proof obligations among threads. You will need that if the non-fixed linearization point occurs while another thread is executing, as I alluded to earlier. All of this leads to fairly complicated proofs that are hard to do and even harder to automate. To overcome this challenge, we suggest to use hindsight reasoning instead of prophecies. And our contribution is to embed hindsight reasoning in separation logic. So what is hindsight reasoning? To do hindsight reasoning, we do the following. We first record facts about the execution history and not just about the current state. So most of the proofs that you do typically are concerned with only the current state of the program, but we add additional information of the past, of the history, which might not longer be true. We use these two types of information or facts to derive inevitable facts. So what we want to do is, if we know that some fact P has been true in the past and some fact Q is true now, we want to derive a new fact R that has been or is guaranteed to have been true in the past. And we want to do this is if every execution that starts in P and then is headed towards Q, it has to pass through R. If you're thinking, so in terms of the state transition system or the configuration graph of the program, this would mean that if that any path from P to Q must go through R. So execution kind of cannot bypass R on its way from P to Q. This type of hindsight reasoning, this generating of new facts about the past of the execution, integrates really well with Wiki-Grease or rely guarantee style proofs because there the interference or the rely and guarantee sets that you capture give you the state transition system or a sufficiently precise over-approximation of that. Now that we know what hindsight reasoning can do for us, I would like to convince you that it's also useful in practice and show you a more formal account of the linearizability argument from our previous example. I'm not showing you the actual implementation of a concurrent set here. I just put here some commands that such an implementation would have executed in our previous example. So as before, we start by traversing the data structure, and the first node we reach is the node X. And at this point, what we do is we record this information in a past predicate. So we kind of copy everything we know in the current state into a past predicate so that we can remember that at some point during the execution, X has been reachable. We do that because of interference. As we've seen earlier, the interference can change the current state. It can, for example, unlink X. While the interference can change the current state, it cannot change the history of the execution. So whatever the interference does, we still know in the proof that X has been reachable at some point. And from there, we just follow the traversal. The traversal will, as a next step, find that in this node X, the value 3 is stored, and decide to continue its traversal and traverse to the successor of X, which is Y. At this point, as you can see, we learn that the successor of X is Y only in the current state. We do not learn anything about the past because we don't know whether or not or what the successor of X has been in this past state that we recorded. Next, we again inspect the node that we are currently traversing. We find that the value 7 is in Y, and now we would like to answer our membership tree and say that 5 is not contained in the set. However, we have no witness for this yet, because in the current state, we do not know anything about the contents of the set really, because as we saw earlier, the nodes X and Y might have been unlinked. And in the past state, we don't know what the successor of X is, so we don't know whether 5 is contained or not. And this is where we apply hindsight reasoning. So we derive a new fact about the past state that says that X has been reachable at this point and its successor has been Y. And in this state, we can derive that 5 is not contained in the set. How do we do that? Well, intuitively, you can think of the last moment the node X has been updated. Because we currently see that X is pointing to Y, this last update must have installed Y as the successor of X. And by this temporal invariant that says that unreachable nodes never change, we know that X must have been reachable at that point in time. Hence, our conclusion in hindsight is correct. And as I said, this new past predicate that we derived now gives us a witness for the fact that 5 has not been in the set at some point in time, because value 5 would need to go between 3 and 7 because the set is sorted, and as we can see, it is not contained here. And this establishes our linearizability proof obligation from earlier. So with that, display of what hindsight can do or how we can use it in a proof, I would like to tell you a bit more about our technical contributions in the proof, in the paper. We presented an abstract of Wiki's separation logic, and we integrated hindsight reasoning in form of what we call the temporal interpolation rule. And it does exactly what we've seen so far earlier in the example. If we know that some fact P was true in the past and Q is true now, we can derive a new fact R about the past of the computation if we can interpolate P and Q to this new fact R. We also give several ways to determine whether this interpolation is true or not. One of the, I would say, more handy ones is this strategy using a temporal invariant as the one you've seen. Such invariant I needs to be implied by P. It needs to be interference-free in the standard Wiki sense, so it needs, so no interference must invalidate this predicate, so no step in the program must invalidate it. And together with now Q, the invariant must imply that past or that R has been true at some point during the history or during the execution. And of course, we showed that our program logic is sound, so especially that the temporal interpolation proof rule is sound. And I think our proof is quite interesting because we do it by eliminating this proof rule from the proofs that use it. So what this means is that temporal interpolation really is a proof structuring mechanism. It doesn't allow you, so temporal interpolation does not allow you to prove more, but it allows you for simpler proofs. And all of that we implemented in a tool that automatically checks concurrent data structures for linearizability, and it uses temporal interpolation to deal with non-fixed linearization points. And you can see our benchmark set on the right-hand side of this slide. And I want to turn your attention to the last row here, the logical ordering tree. It's a fairly complicated concurrent set implementation that uses a doubly linked list and a tree superimposed onto it to speed up lookups. And what we found while we tried to verify this implementation is that the original implementation contained a bug that hasn't been reported yet. We also found a bug in a previous proof attempt that was a pencil and paper proof attempt, and it didn't use a program logic. So altogether, our proof in the paper is the first proof of the fixed version of the logical ordering tree, and we are confident that this proof is correct because it is also generated by our tool. And with that, I thank you for your attention.
Hi, I had a small question about the ability of your tool. So the standard data structures proven by prophecy is RDCSS and the Harling-Wing-Q, and I was wondering if your tools has the ability to automatically verify those two data structures as well?
No, for the Harling-Wing-Q, we do not have arrays, and for the RDCSS, we also do not have that. We are more focused on, like, I would say, traditional data structures. Also, the reason for RDCSS is that there is this non-fixed linearization point for it's an impure non-fixed linearization point, and we cannot handle this. So at the moment, our proof system can only deal with pure non-fixed linearization points. We believe that you can extend it really easily to impure non-fixed linearization points, but we haven't done this so far.
Okay, and my second question is whether your approach will extend to weak memory models as well, where hindsight reasoning is especially difficult to do due to weak memory effects?
We haven't looked into that. I mean, we really want to do that, but we haven't looked into it right now.
Right, thank you.
Thank you. It's very elegant work. So part of my question was already asked by the previous one, so I was about to ask whether this is complete with regard to prophecy-based reasoning, barring the fact that you are geared towards automation. And I think the answer to that is no. But could you please elaborate, what do you mean by non-pure, non-fixed linearization points that you cannot support?
What non-fixed linearization points are?
No, I think you said pure non-fixed linearization points.
Oh, yeah.
And could you, like, I'm not familiar what is the purity in non-fixed linearization points.
So
could you please elaborate on that?
I'm sorry, I don't get the beam again. So with impure, I mean that it alters the logical state of the data structure. So for example, inserting or removing. So truly inserting and extending the logical contents would be impure, and pure would be things that do not modify the logical state. So for example, the contains method that we saw would be completely pure, because even if it would update the structure, it would not change the logical contents.
Thank you.
Jean Pichon, Ross Universität. So this work where you sort of keep track of the history of a data structure kind of reminds me of some work on some separation logics that did that. I think in particular by Ilya Sergey and some other people. But it's like the thing isn't very clear in my head, but do you know how this relates to that?
I think, yeah. So there are definitely there have been logics that explore this idea, but I think the thing that we're adding here is really the idea of using hindsight reasoning and giving you this ability of temporal interpolation. I think this is like the key innovation of our work. Does that, I mean, you don't like satisfied by my answer?
Well, I don't fully remember the details, so it's difficult. Maybe we should chat offline.
Okay, sure.
Thank you.
Hey, Peter Müller, ETH Zurich, so very nice work, thank you. I was wondering, could you say a bit more about your tool? So you say it's automated, so what is the input really, I mean, what does the user have to provide, and then which steps are actually automatic?
So the user has to give the program code, obviously, and you have to provide a kind of a node local structural invariant. That's kind of lightweight, so you have to just say what every node in the data structure usually satisfies. And we are using the flow framework, so you also have to say what exactly like the data flow in the heap graph is. And from there, everything is automatic. So if you think of a proof outline, every step in the proof would be fully automatic.
Okay, thank you.
Hi, Zhongye Wang from Yale. Great talk. And so in your work, you can prove the data structure to be linearizable. And I'm wondering what kind of specification you are using. Like you want to prove the data structure that its trace has some kind of properties, right?
So what properties? What
kind of specification you make about the trace? The history of the data structure. Yeah.
Okay, sorry, can you repeat the question?
Yeah, so like you need to give a specification for a data structure and you want to prove it in your framework. And what kind of specification can you like?
So our tool is limited to set data structures at the moment. So to set ADTs, but our theory is not. So our theory is you can, the way we work, you can give it a specification of your choosing.
Okay, and another question is like, do you think you can scale your framework to set linearizability and even interval linearizability, where your actions can be non-atomic?
No, I think we need to be, it's kind of relates, our approach kind of relates to atomic triplets, so the specification needs to be atomic.
Okay, thank you.
Cool. So I have one. So with the bug you found in the LO tree, have you confirmed with the authors that they agree that it was wrong, or have you?
No, we have not, but we draw a lot of nice diagrams. So I don't know if there's an updated version of the LO tree, but in the original paper, it is definitely a bug.
Okay, cool. And so I think probably this is answered by the other things, but there's like this time-stamped stack and queue type data structures where they do things. I'm guessing that doesn't fit as well because it doesn't have a fixed linearization, pure fixed linearization point.
I'm not sure about that. We didn't look into the stacked, to time-stamped stack. I'm not, from the top of my mind, I think it's not strictly linearizable, but there's some weaker form of linearizability, but I'm not sure. We haven't looked at this particular.
I think it's linearizable, but the linearization occurs like after the method. Deciding occurs after it's terminated the method.
Yeah. So at the moment we have focused on pure non-fixed linearization points, but I believe we can lift this to non-fixed, impure non-fixed linearization points.
Cool. Okay, let's thank the speaker.
Thank you.